Welcome to today's lecture. In today's lecture, we shall study the Lagrange interpolation formula. Lagrange's interpolation formula is actually an advanced technique than the Newton's interpolation formula of determining a polynomial which agrees with a given set of tabulated values. In Newton's interpolation formula, we were given actually the set of n plus 1 pointers, namely x0, y0, x1, y1 to xn, yn. Then we were determining a polynomial of degree n which agrees with these n tabulated pointers. But the drawback of these n tabulated pointers was that this x0, x1 to xn, they must be equally spaced. But now that condition is dropped in the Lagrange interpolating formula, if we are given these n plus 1 pointers without xi's being equally spaced, then we can find out a polynomial of degree n which agrees with these n tabulated pointers. So now let us start doing this Lagrange interpolating formula. Let y of x be a differentiable function which is n times 1 differentiable at least in the interval ab. We consider a set of n plus 1 pointers x0, y0, x1, yn to xn, yn, where xi's need not be equally spaced. If they are equally spaced, then it's all okay, but if they are not equally spaced, still we can use Lagrange interpolation formula here. So our problem here is to determine a polynomial of degree n, which we shall name as Ln of x that agrees with y of x at these tabulated pointers. But here we do this exercise step by step. We will step by step first define a Lagrange's linear interpolating polynomial. So we will first study the linear Lagrange interpolating polynomial. Then we will come to define the quadratic interpolating polynomial. Then similarly we can define the cubic interpolating polynomial and go to the higher degrees. And then finally we can define the nth degree. Now for linear interpolating polynomial can be used when we are only given two tabulated values x0, y0 and xn, x1, y1. If we are given only 2 points, then we can find a linear interpolating polynomial. If similarly we are given 3 points x0, y0, x1, y1, x2, y2, then we can find out a quadratic interpolating polynomial. Now for cubic interpolating polynomial we must be given 4 pointers, and similarly if we are given n plus 1 pointers, then we can define the nth degree Lagrange's interpolating polynomial. So Lagrange's linear interpolation formula. We are given 2 points x0, y0 and x1, y1. The Lagrange's linear interpolation formula is given as L1 of x, which is equal to L0 of x, y0 plus L1 of x, y1. Now here L0 of x, it is defined as x minus x1 by x0 minus x1 into y0, which is a given value, and plus x minus x0 divided by x1 minus x0 into y1, and again y1 is a given tabulated value. So here in this formula we are given x0, x1 is given, y0 and y1 is given, that we need to substitute here to obtain this L1 of x as a linear Lagrange interpolating. Similarly, now let's first move towards the quadratic Lagrange interpolating formula, or we can say Lagrange interpolation formula of degree 2. Now for this formula we need 3 points x0, y0, x1, y1, x2, y2. They are given. Then the Lagrange's quadratic interpolating formula is given as L2 of x equal to L0 of x, y0, L1 of x, y1, L2 of x, y2. So we are given 3 terms here. But now L0 of x, L1 of x, L2 of x, they are defined slightly differently. L0 of x is defined as x minus x1 into x minus x2 divided by x0 minus x1, x0 minus x2. Similarly, L1 of x, it is x minus x0 here, x minus x2 here, divided by x1 minus x0, x1 minus x2, and similarly L2 of x is defined in this way. But now it seems to be difficult to remember this formula for L0 of x, L1 of x, and L2 of x, but here is an easy way to understand it. So how do we remember or understand this L0 of x, L1 of x, and L2 of x? And similarly we can do them for the higher degree Lagrange interpolating formulas. Now in this case, when we are given 3 pointers, then for this quadratic interpolating formula, this L0 of x, we keep in mind 3 pointers. These three objectives x minus x0, x minus x1, and x minus x2. For L0 of x, we write only x minus x1 here into x minus x2. We skip x minus x0 here. So first let's look at the numerator for all the 3 terms. Now for L1 of x, we just write x minus x0 into x minus x2. So we skip x minus x1. For L2 of x, we write x minus x0 into x minus x1, and we skip x minus x2. So let's again come to L0 of x. So we have skipped in the x minus x0 in the numerator. So we write only x minus x1 into x minus x2. Now in the denominator, we just replace this x by x0. So we write x0 minus x1. Replace this x by x0. We write x0 minus x2. So that's L0 of x into y0, which is a given point. Now L1 of x, we skip x minus x1 in the numerator, so we write x minus x0 into x minus x2 and replace this x by x1, this x by x1 in the denominator. And similarly for L2 of x, we skip x2 and we write only x minus x0 into x minus x1, then replace this x and this x by x2 to write on the denominator of Lagrange's interpolating formula of degree 2. Similarly, we can define the nth degree Lagrange's interpolating formula. Here we must be given n plus 1 pointers, x0, y0, x1, y1 to xn, yn, which are n plus 1 pointers. Then Ln of x, which is the Lagrange's nth degree interpolating polynomial, which is now defined as L0 of x, y0 plus L1 of x, y1 plus Ln of x, yn. Now in Li of x, in the numerator we write x minus x0, x minus x1, all of these multiples, but we skip x minus xi. So we have skipped x minus xi in the numerator of Li of x. Then in the denominator we replace this x by xi here, so we write xi minus x0. For this we replace xi here, xi minus x1. This is x minus xi minus 1, denominator is xi minus xi minus 1. And similarly x minus xn, denominator is xi minus xn. Now here we have a very nice property for this Li of x. This Li of xg, this becomes 0 when I is not equal to j, and this becomes 1 when I is equal to j. That we can easily see here. Or suppose if we take an example of L2 of x. L2 of x, as we define it, like L0 of x y0 plus L1 of x y1 plus L2 of x y2. Then suppose let us define, but how do we define this L1 of x? As we will skip now x minus x1 only, so we write x minus x0 into x minus x2. Now for the denominator we just replace this x by x1, so it's x minus x0 into x1 minus x2. Now here we can easily see that L1 of x0, now we will get x0 minus x0 here, x0 minus x2 here, so this will be equal to 0 because x0 minus x0 will be here. Similarly L1 of x1, now this will be x1 minus x0, which will be cancelled with the denominator. Here we will get x1 minus x2, again cancelled with the denominator, we will get this to be equal to 1. And sorry, this is L1 of x2. So we will here get x2 minus x2, which is equal to 0. So that means L1 of x0, L1 of x2, they are both 0, and when this index and this index is same, then the value is 1. So that is what we define here. Li of xj is 1 when I is equal to j, otherwise this is equal to 0. So this was the Lagrange's interpolating formula for degree 1, degree 2 and degree n. Similarly we can define the degree 3 and degree 4 and so on. Now let's come to this example. Using Lagrange's interpolation, find a polynomial that passes through the points 1, 3, 2, 7 and 4, 20. So we are given 3 points here, which we shall name as x0, y0, which is 1, 3. Then x1 is 2, y1 is 7, and similarly x2, y2, which we call as 4 and 21. Then we can define the Lagrange's quadratic interpolating formula because we are given 3 points, so we can find out a quadratic interpolating formula which we define as L2 of x equal to L0 of x y0, L1 of x y1 plus L2 of x y2. And now let's again repeat how do we define this L0, L1 and L2 for the sake of practice. L0 of x, we will skip x0 only, so we will write x minus x1 into x minus x2. In the denominator we write x0 minus x1 into x0 minus x2 and multiplied by y0. Now for L1 of x, we skip x minus x1 only, so we write x minus x0 and x minus x2 whole divided by, now replace x by x1, so it's x1 minus x0, x1 minus x2 into y1. Then plus L2 of x, we skip x minus x2, so we write x minus x0 into x minus x1 whole divided by, now replace this x by x2, so we get x2 minus x0, x2 minus x1 into y2. So that is the formula for L0, L1 and L2. So it is given here. Now we just need to replace the values. Now first we have x minus x1, and x1 is equal to 2 here, so it's x minus 2. X minus x2, x2 is equal to 4 here, so we have x minus 4. Similarly in the denominator we have x0 minus x1, x0 is 1, so we have 1 minus 2 in the denominator and 1 minus 4, which is x0 minus x2. We just replace the values. Now after calculating the next step, so x minus 2 into x minus 4 is there, 1 minus 2 is minus 1, 1 minus 4 is minus 3 into this 3, which is the value for y0. then x minus x1 into x minus 4 by 2 minus 1 is 1, 2 minus 4 is minus 2 into the 7, which was the value for y1. Similarly, x minus 1 into x minus 2, 4 minus 1 is 3, 4 minus 2 is 2 into 21, which is actually the value for y1, y2. Okay, then the next step is, okay, so here we can see this minus 1 into minus 3 is plus 3, so this will be cancelled. This will become 7 by minus 2, x minus 1 into x minus 4, 7 by 2, x minus 1 into x minus 2. Then simple calculations yield us this product. This is equal to x square minus 6x plus 8 minus 7 by 2, x minus 1 into x minus 4 is x square minus 5x plus 4. Again 7 by 2, x minus 1 into x minus 2. There's x square minus 3x plus 2. Now after simplification we get this as x square plus x plus 1. So this is our required L2 of x. So we have obtained L2 of x as x square plus x plus 1. Now first let's verify if we have done all of the things correctly. The given 3 points were 1, 3, the second point was 2, 7, and the third point was 4, 21. Now let's see if this x square plus x plus 1 satisfies all these 3 points. For that thing we will try to evaluate L2 of 1, L2 of 2, and L2 of 4. Let's see if we get the proper values. So L2 of x1, that is 1 plus 1 plus 1, which is 3, which is our required y naught. Now L2 of 2, that will be 2 square plus 2 plus 1, which is equal to 7, which is our given y1. And similarly L2 of 4, that will be 4 square plus 4 plus 1, which is equal to 21, which is the correct value for y2. So that means we have properly calculated the quadratic Lagrange interpolating formula. Now we have mentioned some more exercises here. From the following data we are given the value of x and f of x. So x is the input value minus 1, f of x is also minus 1. If x is 0, then fx is also 0. If x is 1, then fx is minus 1. If x is 2, then f of x is 2. We need to find out the value of f of 3 using Newton's interpolation formula as well as using Lagrange's interpolation formula. Here in this we are given this is actually x0, this is x1, this is x2, and this is x3. These 4 points, they are actually equally spaced. So we can use Newton's interpolation formula as well as we can also use Lagrange's interpolation formula. And we will also compare the conclusions using these two different methods. And now we have another exercise. Find a polynomial p of x that satisfies the following data. We have x is minus 1, then p of minus 1 is 1, p of 0 is 1, p of 1 is 5, and p of 3 is 19. Now here we will try to find out the polynomial p of x which satisfies all these 4 points. So obviously we will find this, since 4 points are given, so we will find a cubic Lagrange interpolating formula. So we will apply the Lagrange method because x0, x1, x2, and x3, they are not equally spaced. And here we will also explain why Newton's method cannot be used in this case. And the simple reason for that is the Newton's method cannot be used because the input values minus 1, 0, 1, and 3, they are not equally spaced. In fact, minus 1, 0, they are spaced by 1 units, 0 and 1 spaced by 1, but 1 and 3 they are spaced by 2. So therefore Newton's method cannot be used. So the only method that we have in hand is the Lagrange method.